Welcome to springlib.
So first we want to graph the function f of x is equal to sine of x raised to the sine of x. Then we want to explain the shape of the graph by computing the limit as x approaches 0 from the right and as x goes to infinity. Then in part C, we're going to estimate the max and mins from the graph we made in part A. And then we want to use calculus to find those values exactly. And then lastly, we want to graph the second derivative to estimate the x coordinates of inflection points. So I went ahead and already graphed f of x, and you might notice that I only really labeled this first tilde kind of looking shape. And if you were to graph going out on either side, it just repeats this tilde shape over and over again forever. And you might notice that the next tilde starts at 2 pi and then is going to end at, so I didn't write this on here, but let me go ahead and write it real fast, at 3 pi would be this other endpoint. So it kind of looks like these tildes are periodic with 2 pi. So if we just figure out everything for this first tilde looking graph, then we will know all of the values for it on either side. So let's just go ahead and write those out really quickly. So our maxes, or actually we're just supposed to find what the max and mins are, which I already did. But we will need to know that this is periodic 2 pi for when we're finding the values exactly in part C, as well as estimated our inflection points. So once we find those just on this first period here, we know we can just add 2 pi k, where k is some integer, to get the rest of our solutions as well. All right, so now for part B, let's talk about the behavior as x goes to infinity. So just by looking at the graph, you might notice that since it is periodic, it never really gets closer to any value since the values just keep repeating. So from that, we can conclude that sine of x to the x is just going to diverge. So it's not going to get really close to anything. And then if we look at the graph here, it looks like that, or at least the graphing calculator that I used, says that the value for 0 should be 1. So let's see if we can actually show that the limit as x approaches 0 from the right is going to be 0. And something I'm just going to do is move this up into this corner right here so I can just work down as opposed to having to go sideways. All right, so let's just go ahead and apply this directly first. So if we were to just apply it directly, well, sine of 0 is defined, which is just going to be 0. So it's going to be 0 to the 0, and I have no idea what that means. But anytime we have something to 0 to the 0, we can use e and natural log to rewrite it. So let's go ahead and do that. So limit as x approaches 0 from the right. So I have base e now, and then I'm going to take the natural log of sine of x to the sine of x, which I can rewrite as sine of x natural log of sine of x. And again, let's just go ahead and apply the limit because maybe we get something that works a little bit better. So this is going to be e to the, well, sine of x again goes to 0. Natural log of something going to 0 is going to be negative infinity. And again, I don't know what 0 times negative infinity is. So let's go ahead and rewrite this, because anytime we have 0 times infinity, that means we can rewrite this to use L'Hopital's rule. So the limit as x approaches 0 from the right of e to the, so I'm going to rewrite this as 1 over sine of x. And then that would be like I'm dividing it, but that's the same thing as just dividing by cosecant. So I'm going to rewrite this expression now as the natural log of sine of x over cosecant x. And then just one more time, let's go ahead and apply this. So again, our numerator is going to be negative infinity, and then our denominator is going to go to infinity. Because remember, cosecant is just 1 over sine. And since we're approaching from the right, all the values for sine should be positive. So we have negative infinity over infinity. So that means let's apply L'Hopital's rule. So this here is going to be equal by L'Hopital's to the limit as x approaches 0 from the right of e. So the derivative of natural log sine of x, so it's going to be 1 over sine of x times the derivative of our inside, which is sine of x, so cosine x. And then this is going to be all over. Let me go ahead and scoot my e down a little bit. And the derivative of cosecant is going to be negative cosecant cotangent. Now notice that cosine of x over sine of x, well, that's cotangent. So in our numerator, we already have cotangent. So the cotangents will cancel out. And then we can rewrite cosecant as, or 1 over cosecant as sine. So we can go ahead and rewrite this as the limit as x approaches 0 from the right of e to the negative cosecant x, or negative sine x, since we went ahead and reciprocated it again. All right, now we can go ahead and apply this again, because we know sine of x goes to 0. So it's going to be the limit as x approaches, or so since we apply it, the limit goes away, and it's going to be e raised to the 0, which is just 1. And then that also explains the behavior as sine goes to pi, or any multiple of pi. All right. So we went ahead and showed that. So let's go ahead and find our max and min values exactly. So to do that, remember, we're going to need to find the derivative of this graph. So anytime we have something like this, we can still use that exponentiation trick to rewrite it into something that's a little bit easier to work with to take the derivative. So let's do that. So I'm going to rewrite this again as e sine of x natural log of sine of x. Now let's go ahead and take the derivative of this. So f prime of x. So we're going to have to take the derivative of this using chain rule. And remember, chain rule says we take the derivative of our outside function, which is just going to be e to the x, and the derivative of e to the x is e to the x. So that doesn't change at all. So sine of x times natural log of sine of x. But then we need to take the derivative of our inside function, which is sine of x natural log of sine of x. And then I'm just going to rewrite e to the sine of x natural log sine of x as sine of x to the sine of x, just to save a little bit of space. And now to take the derivative of sine of x times natural log sine of x, we're going to need to use product rule. So remember, product rule says we leave the first one alone. So it's going to be sine of x, then times the derivative of natural log sine of x, which we already found over here to be just cotangent of x. So let's go ahead and write that down. Or better yet, let's write it as cosine of x over sine of x. And then we're going to add this 2 when we switch the order of these. So it's going to be natural log of sine of x times the derivative of sine of x, which is cosine of x. So now notice that here those sine of x's cancel out, and we can factor out a cosine of x. So let's go ahead and do that. So sine of x raised to the sine of x times, so we factored out that cosine of x on the inside, so we have the cosine of x here. And then factoring that out, we'll have 1 plus natural log of sine of x. All right. Now, to find our critical values, we're going to want to set this equal to 0. And if we go and look at our original graph again, we can see that sine of x to the sine of x never becomes 0 at any point. So that will never be 0. So when we apply the zero product property, the only numbers, or the only things we actually need to set equal to 0 are cosine of x and 1 plus natural log sine of x. So let's go ahead and do that off on the side here. So we have cosine of x is equal to 0, as well as 1 plus natural log of sine of x is equal to 0. So cosine of x is equal to 0 at pi half, 3 pi halves, and really anything pi half plus pi k. So let's go ahead and write that. So we know x is equal to pi half plus pi k. And if we were to just go ahead and plug in pi half into here, doing that will give, so f of pi half, because remember, if I add pi k to this, it really should just give me the same answers. And doing that, it will be, well, sine of pi half is 1. And sine, again, is going to be 1, so it's 1 to the 1 or 1. And if we were to go and look, we have pi half to the first power, or pi half, and we get our output of 1, so that matches up with what we would expect. And now we can go ahead and solve over here for our other values. And doing that will give us, so first subtract the 1 over, get natural log of sine of x is equal to -1. Exponentiate each side, giving us sine of x is equal to e to the -1. And then we would take arc sine of this. So we get one solution that's going to be x is equal to arc sine, actually I'll just write this as sine inverse. Sine inverse of e to the -1. And we get a second solution being x is equal to pi minus sine inverse of e to the -1. And so remember, we get that other pi answer from, if we were to just draw a unit circle right here. So if this is where e to the -1 is, over here would be another solution for it. So we end up with those two values, and they should give the same output for us. And now we could go ahead and figure out what this value should be exactly. Since they should have the same one, we could just go ahead and plug in one of them. So f of sine inverse of e to the -1st power well, this is going to be, well, sine of sine inverse, well, those just cancel out, and we have e to the negative first power. And then the same thing in our power here. So we have e to the negative first power raised to e to the negative first power. So that would give us our actual minimums. And then again, if we wanted, we could just go ahead, like I was saying at the start of the video, add plus 2 pi k to each of these values here. And it would give us all of our answers for where all of our minimums are going to occur at. All right. Now for the last part. So we were supposed to graph the second derivative, and as you can see here, that's pretty long, and it would make the video much too long. So I just went ahead and found the derivative already using a derivative calculator, and since we've already used the derivative calculator for some of the earlier problems, I really didn't have much problems with my conscience of just plugging this into a derivative calculator to find that. And after I did that, I went ahead and graphed it, and I found just the x-intercepts on the first period, so from 0 to 2 pi, or from 0 to pi, which occurred at about 0.95 and 2.2. And so we can see that on either side of these, so to the left of 0.95, the function is going to be concave up because f double prime is strictly larger than 0. And to the right of this is going to be concave down since f double prime is strictly less than 0. And then to the left of 2.2, it's concave up. So each of those do end up being points of inflection. So we know that at 0.95, we will have one, and about 2.2, we will have points of inflection. But then again, we're going to need to add plus 2 pi k to all of our answers here, because of the periodicity of this. And so just remember again, this k is just an element of the integers.